Okay, then we will get into the components of an AC motor. How many people in here is full with AC motors? I'd say everyone in here. If you've ever been around a sewer plant or lift station or water plant, you've seen an AC motor running. And they can be from, tiny. The little vibrators in your phone's probably run by, it's probably a little DC motor, but motors range from small to humongous. I've seen pictures of motors up to 345,000 horsepower. So there is some large equipment out there. And it was being worked on where I seen the picture at. So there's large and small equipment all over this area. And this equipment's got to be maintained. But we're going to go over some of the components of a three-phase motor here and let you look at it. How many in here has ever seen a three-phase motor apart? Okay, well if you look at page 5 in your book, it's going to show you what we're looking at. And what we'll first look at is the case. That's just the housing of the motor, and they're from anything from cast iron to aluminum to rolled steel. I'm trying to think if I've ever seen one that was made out of plastic. I'm pretty sure I have. But the construction of this outer shell can be anything. This is probably the most common that we see is this rib fin, and we call that the motor housing. So it's a pretty, I use this stuff every day, so I'm going to talk in terms that you all probably don't have a clue what I'm talking about, but I will try to explain what we're doing. And at the end of the day, I know we're talking about troubleshooting this, but we have to understand, or I do, have to understand what these components do inside the motor and what they do so you understand what to look for. But if you'll see here, you see your windings in there, right in there. I'm a little shaky, I'm a little nervous, so y'all don't mind the red dot jiggling around. That's your stator windings. That is the copper. And those copper wires is just wound in loops and inserted in that. Then you have your core, which is, we would call that the stator core. It's made up of laminations, real thin layers of steel, all put together. And those pieces of steel is all insulated from one another. So, just saying that right there is probably 200 pieces of steel layered in there together. When those two pieces of steel touch, you got a hot spot. And that hot spot can cause your motor to fail too soon. But that's pretty rare. It takes a bunch of the hot spots to create enough heat to cause a problem. But in theory, that can cause problems. The insulation in that can deteriorate and cause problems. I'm going to get my buttons there. Okay, we have a rotor and shaft. You see going right through the middle. The rotor is pretty much a chunk of steel. Most of them has either got aluminum or copper. The aluminum bars are usually inserted in it. Actually, most of your squirrel cage rotors is die casted with aluminum, so it's extruded in there. And you've got a chunk of steel with and your aluminum or copper makes the conductivity to make it magnetize. So now you'll see your bearings. You've got a bearing on each end of the motor, which is usually what we see in all motors. Usually you've got 2 bearings. You might see 3 occasionally, but most of the time it's 2 bearings. Drive in, opposite drive in. You'll hear this term used probably quite a bit today. You drive into the motor, your output in. We hear people all the time call front and back. Well, that nomenclature is horrible because manufacturers call different things different. So we use the term drive-in, opposite drive-in, pretty simple. But you got your output shaft, you've got a bearing, then you've got your housing here. bearing housing, usually held on by bolts. The, got a fan shroud back here. The fan here, when this motor spins, all it is a cooling fan, so it creates airflow blowing across the motor. As this motor generates heat in here, where all this energy is being used to create horsepower, create power, it's going to create heat. Anytime we make energy, we're going to create heat. This heat's got to go somewhere. So it dissipates itself out through the housing of the motor. Your fan blows air right over the motor, blows the heat away. How many people's ever seen these fans right here stopped up? Stuff piled all over them, stopped up. You're reducing the life of your motor because you're reducing the cooling. Of course, you got bearing keepers on each end. Usually some motors have them, some motors don't. You can see them right in there, and I apologize for the bad pictures, but it's about the best I can come up with. So, but anyways, you've got bearing keepers here on this particular motor. You'll see usually you've got bolts that holds that in, and that just holds the position of everything in the motor. Sometimes they don't even have them. I've seen up to 200 horsepower motors that don't even have bearing keepers. Just the end shields hold them on, which is fine. But it's just different design, different applications require different motors. Feet, you know, that's pretty self-explanatory. Lifting, we'll talk a little bit about the lifting eye bolts. Always make sure they're sound. Back on safety a little bit, make sure they're sound. Anybody got any questions about a horizontal AC motor? The components that make it up.
How often should you grease one?
Well, that's a good question. Whatever the manufacturer says. Now, theoretically speaking, I would say anything, and this is me giving my opinion on this, because there's lots of them. It depends a lot on the application, but a motor should be lubricated if it's running 24 hours a day, 7 days a week, probably once a quarter.
Couple shots?
Yeah, not much. You don't want to over-grease. You would be surprised at how often over-lubrication causes the motor to fail prematurely. I mean, we have literally got 10 horsepower motors in before that had 5 pounds of grease in them, inside the motor.
Now, I add to something. I know a lot of our new equipment is something that I've kind of been trying to get more educated on. A lot of our manufacturers have suggested a lot of times on your motor you'll have your alumite, but then also you'll have your drain to take that drain out to when you purge through so you don't over-grease.
Right. And that is a good practice. Most people don't ever do that. They don't go to trouble to pull the vent plug out to let the old grease purge out. In a sealed cavity, when you pump that grease in there, you're creating pressure. Of course, it shouldn't be a sealed cavity, but it's going to create pressure. If that grease ain't got anywhere to go, that bearing is just going to heat up because it's packed in around it. So, the more heat you get, heat is a killer in electric. No matter what the piece of equipment is, heat is a killer. So you want to try to minimize any heat that you can get. Any other questions on horizontal motor? We're going to look at a vertical motor here. It's pretty much the same thing as a horizontal, except it's turned up, mounted vertically. You see a lot of these. How many people in here uses these? They're mostly there about all water plants. Most of them you see, or a lot of them you see, is hollow shaft on a vertical turbine pump. Pretty basic design. You've got a motor, same design as we've got up here, except it's a hollow shaft. Your pump line shaft runs up through the motor. You've got a coupling that sits up on top of this motor. And you couple it to your pump shaft and adjust your clearance height on your pump. let her go. On these, most of the time, as you'll see, you've got most all your pressure in a vertical bearing is hung from the top. As you can see, you've got 2 rows of bearings up here. It's a double row, or what we would call it, it's actually a tandem set of angular contact bearings. And what that does, that makes that motor shaft, the weight of that, hang on there. And most of the time, all of the weight of that pump and the motor shaft, that pump line shaft, all of that weight and thrust is carried by those bearings. Right there. Because if you'll notice in your pumps, there's nothing in them. There'll be some guide bearings down through there, but there's never any more thrust bearings or anything to support that. All your support is done from the top of the motor on that pump shaft. So if you get a pump shaft that's 100 foot long, 16 inch, 24 inch impellers hanging on the bottom of it, 10 of them, it's a lot of weight. But anyways, it's pretty much the same thing. These usually run in oil. You've got an oil bath that these run in, just a turbine oil. People ask all the time what kind of oil to use, just a turbine oil. Whatever the manufacturer specs is what you're supposed to use, but just basically any turbine oil will work fine. If you've got oil in there, try to use what you've got in there. If you don't have the same oil, remove that oil and replace it with whatever you use. Don't mix. But anyway, pretty much the same thing. You got your stator, rotor, and all of that. One other thing vertical motors have a lot in the pumping application is an anti-rotation device. Anybody ever seen these? You ever hear them clicking down when they're coming down to a stop or slowing down or speeding up? You'll hear them click, 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 click. That's that anti-rotation device slowing down. And all it is most of the time it's either peg or steel dowels or ball bearings and an anti-reverse. And as this thing spins, they come up into a cavity and sit there by centrifugal force. And when the force slows down, then they drop out, but it does keep them from turning in reverse. And that's one thing you don't, be careful on startups. I will tell you this, when you're testing the rotation, be careful. Because it's not going to just, don't turn the power on, let's see which side this thing's going to go. You know, just bump your power. Any other questions on the components of an AC motor? Here, we're going to go over single phase a little bit. How many people in here have dealt with single phase motors? How many people hate them? I do too. If I could wire my house 3 phase, I would. I can't stand single phase. It's a nightmare. Look at this. I want to show you something. You see that? What can fail in this? Pretty much 2 bearings and some windings. Pretty simple. You've got some other components that can fail, but they're not going to shut the motor down. Look here, this is a single phase motor. What can fail? There's a switch right there in the back of it. There's another rotating switch. There's a capacitor. Some of them have 8 or 10 capacitors in them. Got another cooling fan inside. So single phase is, you get a lot more components. And they're a nightmare to deal with. A nightmare to repair. Because it can be a lot of things. Really just as simple as a little start capacitor. We love those repairs. But anyway, you got your start capacitor, you got your, then you come down here, you got your housing, you got 2 bearings on each end, shaft, rotor. Then if you'll see right back here in the back, that right there is called a rotating switch. You might have heard them called centrifugal switch. And this part right here that you see mounted in that housing is called a stationary switch. And what these do, as this motor comes up to speed, single phase motors has 2 sets of windings. You have a start winding and a run winding. As this motor comes up to speed, say we're dealing with an 1800 RPM motor, which is the most common RPM that we'll usually see. We're dealing with 1800. This motor will come up and probably come through around the, I'm gonna say from 750 to 1000 RPM range. Somewhere in that range. And what happens is that centrifugal switch, it starts on the start windings. When you energize the leads, the start windings engage. And as it comes up and gets up to some, we'll say roughly 1000 RPMs, that centrifugal switch or rotating switch there opens. Centrifugal force makes it open up. And when it does, you have a set of contacts on this stationary switch that it moves away from and opens. And that drops your start windings out and lets your run windings run. Everyone understand that?
Question.
Yeah.
We have motors that start and run capacitors.
Yes.
Your run capacitors will less microfarad than your
Yes.
starters. So in this case scenario, it's just got a start capacitor only.
Yes, this particular one.
So if it's starting to run, both capacitors are used, does it not have a second winding, or does it still have a second winding?
No, it still has a second.
Okay, so that's second winding. So, and I'm just learning the single phase, because I've never in my, until I started here working with it. If a run capacitor, I guess, fails, do you lose your torque of the motor, or the running of the motor? I guess I'm asking, what can go wrong with the start and run capacitor?
Okay, we'll go over this real quick. The start capacitor is just for everyone's information, a capacitor stores energy. And as it stores energy, as this thing starts, it dissipates that. So a start capacitor will dissipate this energy into the motor, give it a boost to start. If you've ever seen one that the start capacitor is bad, it just hums. And then you replace the capacitor and run fine. A run capacitor is used it stores that energy and puts it back into the run windings as it's running. So it's a boost of energy during the run cycle. Usually a lot of times it's for energy efficiency. It lowers the amp draw of the motor. A lot of times you can take them off and they'll run fine.
Okay.
And
We've had some problems out of them, so that's why I was asking. We got 3 or 4 stations like that, and they had those, and we just,
if you ever, just for instance, and of course we'll probably touch base on it later, but if you ever get out there and your motor's pulling, it's running fine, but it's pulling high amps, could be a run capacitor, on single phase. It could just be a run capacitor, man. You check it and replace it and put it back in here, you drop your amps from 14 to 12. And now we're back down under our overload range. So that's just a thought there, good question. Capacitors is a nightmare.
do they throw them out of phase just a little bit, keeps it out of phase, because that's actually on your starting capacitor. Doesn't that shift the phase, just a little off phase? To get it winding, like a fan, you could flip that thing to run, turn off, put it back up, turn it on, you don't want to run.
Well, what determines rotation on a single phase motor is your start windings. Okay? If you've got your run windings, and if you just plug the motor in with your start windings out of circuit, you can most of the time take it, if it's not under any load, you can spin the fan, or like you would on your air conditioner, you go out there and give it a jump and she takes off. But a lot of times, when it runs on run winding, the motor don't know which way to go. So this time you turn it on, you give it a boost to run one direction. Whatever way you boost it's the way it's going to run. So your start windings determine the rotation of the motor, how you hook those up with the run windings. And we'll get into some of the connections later on and explain the connections and how all that works.
Can you go back to the 3-phase? Because I'm very ignorant when it comes just to the thing. Just explain as far as energy comes in off your lead into the motor.
How does it work?
How does it go?
Okay, here we go. We've got 3-phase, we've got 3 wires coming in most all the time. We'll get into some 6-wire connections later. Anyway, we've got 3 power wires coming in. What everybody's going to see most of the time. and it comes in. You have A, B, and C phase. Okay? Well, as this motor, let's use a 4-pole motor, 1800. Motors are poles determine your speeds. You have 2, 4, 8, 6, or 2, 4, 6, 8, 10, 12, 14, all the way up. That determines the speed of the motor. 2 poles, 3,600, 4 poles, 18, 6 poles, 1,200, 8 poles, 900, so forth, as it goes on. Anyway, but we're going to talk for theory today about 1,800, about this motor. When you energize this winding, you have A, B, and C phase coming in from your power line. All right. In every pole, you have A, B, and C phase. Okay, so this motor goes in, and it's just following a path of electricity through this motor. It's just, these windings are laid in there in circuits.
Does it have a stop and start, or is it continuous?
It's,
The windings, I mean, there's no break in it, it's,
well, yes, there is connections in there, but when you connect the motor, it is a continuous loop. And we'll do some of that later testing. I'll explain that when we go to testing. When you go to own a motor, you've got continuity. If you've got a good motor, 3-phase motor, and you stick you're going to ohm it out to see if you've got resistance. So you've got continuity on any lead. So you've got a continuous circuit through this motor. All right. When you turn the power on here, it creates a magnetic field in them windings. Okay? And it's going in there at 60 cycles per second, which is 60 hertz. That's what we've got in the US, 60 hertz. Now with the drives, we slow her down or speed her up. We run this through these windings at 60 cycles per second, and it comes in and it starts to go around this stator field. Give me just a second. Might be able to explain it better with it.